Hello, in this video we are going to look at a question from an exam from a few years ago. It's related to how the atmospheric pressure decreases as the altitude increases. The question says that it does so by following an exponential decay. So we are studying exponential functions and we want to make a really neat graph of this. So that's one of our main goals over here. But you should pause the video here and read the question carefully. Okay, so it says that for each kilometer you go higher, the atmospheric pressure decreases by 12%. And we assume that the atmospheric pressure at sea level is 1013 hectopascal. So the first thing we want to find is what is the atmospheric pressure 1 kilometer above sea level. So that means that we are talking about 12% decrease of 1013. So we want to multiply 1013 by 0.88 because 0.88 is 1 minus 0.12, so it's a multiplier for a 12% decrease. So if you do this computation in your calculator, you will get approximately 891 hectopascals. So that was the answer for part A. For part B, we want to explain why the function that is given here gives us the pressure 8 kilometers above sea level. So the first thing that we have to look at is that for 8 kilometers that we go up, the pressure is going to decrease by 12%. So we are going to have to multiply by the multiplier we found before, 0.88. And we are going to have to multiply by that as many times as kilometers we go above the sea level. And then kilometers, the altitude above the sea level is given by A. So we're going to need to multiply by 0.88 to the power of A. And the starting point, so this is the multiplier for 12% decrease. And then we need to have a starting point for this exponential function. We need to know what is the pressure when we are at sea level, so when A is equal to 0, and that's given in the problem as 1013. So this is P at sea level. So this is how we make the function that tells us the atmospheric pressure in terms of the altitude in kilometers. So that's the two key points that you need to write to explain what you want. That the 1013 is given by the pressure at sea level, and then the 0.88 is a multiplier for a 12% decrease, and to the power of A because A is the altitude. So that's all you need to explain, and it's fine if you use words to explain that. We want now to find two more points. We want to know what is the atmospheric pressure when the altitude is 5.62. So we want to evaluate our function at 5.62. And we also want to evaluate our function at 8.85. And those are some natural elevations, the highest in Europe and the highest in the world. So we do this in the calculator, and we get that according to our model and approximate to three significant figures, the pressure for A equals 5.64 is 493, and the pressure for 8.85 is 327. Now we want to use the information we have so far to sketch the graph of the atmospheric pressure against the altitude. And the question says that we have to make a neat big sketch using a reasonable scale on the axis. Well, the axes were provided in the exam. I don't have the axis copied here, but we're just going to make the axis ourselves. So here are my axes. On the x-axis, I'm going to represent the altitude in kilometers. I need to label this. And on the y-axis, I'm going to represent the pressure in hectopascal. Now I need to decide the scale that I'm going to use. So the first thing that I have to think is, okay, what kind of values are relevant for our graph? For A, we have values of the function when A is equal to 0 kilometers, that's sea level, then when it's 1, when it's 5.64, and when it's 8.85. So I need for sure to be able to accommodate 9 kilometers in my picture. If I can accommodate a little bit more, not to stop the graph right there, that's fine. But that's all I need. So I'm going to count how many little squares I have here to see how it's the best way to divide them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so just thinking about space I have over here. I think I'm just gonna make that 1 square corresponds to 1 kilometer, and I'm gonna be using most of my axes. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means my graph is gonna end like kind of at 9, almost. Not to have a lot of relevant information after that, but that fits quite well in my graph. Maybe I'm gonna mark 11 here, and then I'm gonna move my graph a little bit over here just because I only need to include what is relevant for myself. So yeah, depends on what is that you have available on your page. I think for me it would work to mark it up to here, and that's reasonable size. Okay, for the pressure in hectopascals, the highest value that we have is 1013 at sea level, and then the values are going to be going down, and then the lowest that I have is 327. So I need to basically be able to fit a bit more than 1000 hectopascals in the y-axis. So let me count 1, 2, 3, 5, 6, 7, 8, 9, 10. Okay, so if I say that is 1 square corresponds to 100, so then over here I have 1000, and I just need to mark a little bit over 1000, so that will be fine. Before let's just add the points that we know. So now let's just, I'm gonna change the color, and I'm gonna add the points that I know, and I'm gonna make sure that the coordinates of those points are clear. We know that when A is 0, P is 1013, so I'm marking the point over here, and I'm gonna be careful to write down what this represents. 0, 1013. Okay, then we know that when A is 1, we found the pressure to be 891, so I'm gonna mark that. If I have 900 here, so it's reasonable to say that 899 is here. So my point is gonna be here. I'm going to show on the axis the 900 right here, and then I'm gonna write the coordinates of the point, so anyone reading the graph can read what this point is. 891. Then I have the pressure for the altitude of 5.64. That will be around here. And that pressure is 493. So I'm going to mark where 500 is. 2, 3, 4, 500 is here. So just under it, and corresponding here, around here will be the point. I'm going to write its coordinates. I can add some lines here to read the graph nicer. I'll do that in 1 second. So 5.64, 493. Let me use another color to add some lines to be able to read the graph more nicely. just thinner lines. I think it will look nicer. I have one here to mark and another one here. I'll mark also the horizontal ones in a second when I have them already. The last point corresponds to an altitude of 8.85 and the pressure is 327. So let me mark 300 here. So 327 should be around here and 885. The point should be around here. And let's continue adding. So now that all the points are ready, I need to think about how this function is going to look like. This is a function showing exponential decay. So the base of the exponential is 0.88, which is a number between 0 and 1. So it's going to look like something like this. So I need to join my points, keeping that general form in mind. So something like this. And I'm going to label my function y is equal to p of a. And this is my graph ready. So I move back to reading the question. For the next part, we want to use the graph to estimate what will be the altitude if we measure the pressure to be 700. And we want to use the graph for that, and we want to show it in the graph. And then we also want to use the calculator to improve that approximation. So I'll move back to my graph so we can use it. I want to see what's going on when the atmospheric pressure is 700. So I'm going to mark 700 over here. And I want to see what is the corresponding point in the function for this pressure of 700. That's over here. And then I want to mark what is the pressure that corresponds to that. So I need to go down and see what that corresponds to on my graph. So I'm reading here that when the pressure is 700, according to the graph, A is around 3. So this is part E. I'm saying that P of 3 is approximately 700 from graph. Now we want to use the calculator to see if that is the case or not. So let me open the calculator here. So I want to know what happens exactly if I evaluate the function at 3 to see if I really get 700 or not. So I need to do 1013 times 0.88 to the power of 3, and I'm getting 690. Okay, this is very close. I wanted to get 700. That means that if I want to get 700, I should try with a number that is smaller than 3, because the function is decaying. So I'm going to try that. I copy this so I don't need to write it again. I'm going to try with 2.9, and that's very close to 700, right? It's not 700 yet. It's still too small. So if I want to get 700 and correct to 3 significant figures, I'm going to have to try with a number that is a little bit smaller than 2.9. So let's try with 2.85. That was too big. So I'm just doing what's called trial and error. Of course, there are other ways of doing this. That's what we know so far. This is still too big. So let me try. Okay. So when A is 2.89, I'm getting that the pressure is 700 correct to 3 significant figures. So I wrote over here the information we got from the calculator and the improved value that we got doing trial and error. I want to quickly go to comment on the last part of the question. It says we have to explain why the graph wouldn't be useful to estimate the atmospheric pressure at an altitude of 10 kilometers. The information that we have is for altitudes going between 0 and 8.85. So if we try to use the graph for a value that is outside that range for 10, we will be doing an extrapolation.